Hey guys, welcome back to the channel. Right now, something extraordinary is happening inside the semiconductor industry. And it's not just the massive demand for chips that we see. The extraordinary thing that is happening is we see the world's supply of silicon wafers being reallocated. This is the structural reallocation we've talked about in this channel. In today's video, I'm going to discuss 6 factors that are driving the reallocation. But before we do that together, we have to watch a video that sets the stage or lays the foundation for why we're seeing structural reallocation in the marketplace today. Let's watch.
Of laptops, the glow of phones, and the invisible vaults of cloud storage are all reportedly facing the same fate. In 2026, the world will stare into the abyss of a memory shortage. By this December, there may not be enough RAM, the basic building block of every computing device, from your smartphone to the supercomputers powering artificial intelligence. Why? Well, because AI is consuming it all.
Guys, as the video said, in 2026, the world may be staring into the abyss of a memory shortage. It sure feels that way. And I know on our channel, or my channel, we've devoted a lot of content focusing on the memory players and what makes them so special, what makes them so differentiated in the market today. But today's video, I want to focus on the structural reallocation. Why is it happening? The video clearly mentioned it at the end. It's because of AI. AI, or artificial intelligence, is consuming chips at a scale that the industry never expected. But here's the interesting part. AI isn't just creating new demand. AI today is actually taking wafers away from other parts of the industry. We see wafers being shifted away from smartphones, PCs, traditional servers, even being shifted away from consumer memory. Inside semiconductor fabs all around the world right now, there is a quiet shift underway. And engineers and executives are not just deciding on what types of chips to make anymore. Now they're deciding on who gets access to the world's most valuable resource, the silicon wafer. Today's video, we're going to focus on a concept that I like to call the Great Wafer Cannibalization. Because literally right now, artificial intelligence is eating its way through the semiconductor industry's supply of silicon. If you haven't done it already, hit like, hit subscribe to the channel. We're going to talk about the 6 factors that are driving the Great Wafer Cannibalization. So let's dive in and let's start first, but let's just look at the process of how to make silicon wafers overall. Guys, as you know, if we can understand this, we'll understand how the cannibalization works from the beginning. These wafers are ultra pure slices of crystalline silicon manufactured by a few companies around the world like Shinitsu, Sumco, and Global Wafers. Each wafer goes through thousands of processing steps like you see on the screen here, well before it becomes a silicon wafer itself. It goes through these steps inside fabs that are operated by Taiwan Semiconductor, Samsung, and Intel. And when the manufacturing process is complete, the wafer contains hundreds of individual chips called dies. But here's the key constraint. The number of chips you can produce on a wafer depends heavily on the die size. Smaller chips mean more dies per wafer. Larger chips mean far fewer. And that's where AI is changing everything. Because right now we have the rise of the monster chip. We know in the past with consumer chips, they were relatively small. A smartphone processor might measure 100 to 120 square millimeters. A laptop CPU might reach 200 square millimeters. But AI chips are a completely different category. Take GPUs produced by NVIDIA. Some of their AI accelerators approach 800 square millimeters. Guys, that is close to the physical limit of what can fit on a silicon reticle. This means that something remarkable is happening. It's the first part of the cannibalization. It's happening at the wafer level. A wafer that can produce 500 smartphone processors now may only produce 60 AI GPUs. But the story gets more complicated because as chips grow larger, the probability of defects increase dramatically. Semiconductor fabs operate in extremely clean environments, but microscopic defects still occur during manufacturing. And when a chip is small, the chance that a defect lands inside it is relatively low. But when a chip is enormous, the chance increases significantly. This means the yield rate drops. So instead of producing 60 working GPUs from a wafer, a manufacturer might only get 40 to 45 usable chips. This is the first mechanism of wafer cannibalization. AI chips simply consume vastly more wafer area than traditional processors. Now let's think about and move over and talk about the economics of wafer allocation. Because imagine that you listening right now, you were the owner of one of the world's most advanced semiconductor fabs. You know your production capacity is limited. You only can produce a certain number of wafers per month. Imagine you have two customers that approach you. The first customer wants to manufacture smartphone processors worth about $50 each. The second customer wants to manufacture AI accelerators worth about $30,000 each. Which customer would you give priority to? I think the answer is pretty obvious. I think the answer is the same for all of us. And it's exactly what is happening inside semiconductor industry today. Companies building AI infrastructure suddenly became the most profitable, important customers for foundries. That means that wafer allocation started shifting towards AI chips. The leading edge nodes like 5 nanometers and 3 nanometers became increasingly dominated by data center silicon. This is another dynamic of wafer cannibalization. The dynamic is that data center economics beats consumer electronics every day of the week. The next layer of cannibalization is the process node level. Only a few companies in the world can manufacture chips at the most advanced node. The leader here is clearly Taiwan Semiconductor. It produces the majority of the world's most advanced semiconductors, and its customers include Apple, NVIDIA, AMD, and others. But the advanced node capacity is extremely limited. Building modern semiconductor fabs can cost $20 billion or more. And even when new fabs are constructed, it takes years to reach full production. So when AI demand surged, the industry couldn't simply just build new capacity overnight. Instead, the existing capacity had to be reallocated. And increasingly, that capacity is going more and more towards the AI accelerators. The next piece we have to drive in and talk about is the memory cannibalization side of this, the memory part of the Great Wafer Cannibalization. Because GPUs aren't the only chips inside of an AI system. In fact, memory is one of the biggest hidden drivers of semiconductor demand. Modern AI accelerators rely on high bandwidth memory, HBM. So let's listen to a video about that right now.
Firms that make nearly all the memory on Earth, Samsung Electronics, Micron, and SK Hynix, are now dealing with demand they cannot keep up with. Micron says demand has far outpaced their ability to supply, and even the entire industry can't catch up fast enough. All of this has one likely outcome: the prices are surging. Market analysts at TrendForce warn drum costs may jump 50 to 55% compared with late last year. That's the steepest spike the market has seen in years. And much of it traces back to the hottest chip in tech, high bandwidth memory, or HBM. And here's the math. For every bit of HBM made, manufacturers give up 3 bits of regular memory, the stuff used in phones and laptops. Meaning AI growth steals capacity from everyday devices.
Guys, that math is pretty simple. Again, if I go back to if you own the fab, what would you do? I mean, your margins are there. High bandwidth memory drive higher margins. It also takes up significantly more capacity. So HBM works very differently from traditional RAM. Instead of a single memory chip sitting on a motherboard, HBM stacks multiple DRAM dies vertically using advanced packaging techniques. Each stack might contain 8 to 12 DRAM layers, and those stacks are placed directly next to the GPU. And here's the surprising part, that an AI server can require hundreds of gigabytes of HBM memory. That means that each GPU consumes enormous amounts of DRAM production capacity. So when DRAM wafers that might have gone towards laptops, smartphones, traditional servers, now they're clearly being redirected into HBM stacks for AI accelerators. This is the memory's version of wafer cannibalization. And there's another part of the factor that the process that we have to talk about, which is the packaging bottleneck. This is the area of industry that many people never think about. After chips are manufactured, they still need to be assembled into the final products. For traditional chips, packaging is relatively simple. But AI processors require extremely advanced packaging techniques. One of the most important is called the CoWoS, and it was developed by Taiwan Semiconductor. So let's dive in and just explain what exactly it is.
Systems on the planet.
Today, it serves as the foundational, non-negotiable packaging technology for the world's most powerful and sought-after artificial intelligence accelerators, including the flagship processors that dictate the pace of global machine learning research. The core unifying premise of the entire CoWoS technology family is the heterogeneous integration of highly complex logic processors alongside massive, towering stacks of high-bandwidth memory, all mounted together onto a single intermediary communication layer known as an interposer, which is then mounted onto a broader package substrate. As large
You guys, so you can clearly see that, as the video mentioned, the CoWoS allows multiple chips to be integrated into a single high-performance package. This is how GPUs connect to HBM memory stacks. But there is a problem. Advanced packaging capacity is limited. And right now, a huge portion of that capacity is dedicated to AI accelerators. So packaging lines that once might have supported other products are now heavily focused on the AI infrastructure. And the final piece of the puzzle is a system-level silicon consumption. A single smartphone contains one primary processor, maybe a few memory chips, and some connectivity silicon. But an AI server is dramatically more complex. A modern AI server rack right now may include 8 GPUs, 1 or 2 CPUs, hundreds of gigabytes of HBM, networking chips, storage controllers, and solid-state drives. When you add everything together, a AI server contains orders of magnitude more silicon than a consumer device. So even if the number of AI systems produced is relatively small compared to smartphones, their silicon consumption is enormous. All of these factors combine to create a powerful structural shift in the semiconductor industry. AI chips are larger. They generate far more revenue per wafer. They require enormous amounts of memory. They consume advanced packaging capacity, and they require far more silicon per system, which means something remarkable is happening. Artificial intelligence isn't just creating a new semiconductor market. It's reallocating the industry's most valuable resource, the silicon wafer. And that's why the Great Wafer Cannibalization may become one of the defining trends of the semiconductor industry for the rest of the decade. I hope you guys enjoyed the video. Drop some comments below. Let me know your thoughts on the Great Wafer Cannibalization. Have a great Saturday. See you soon.